All right, guys, let's get started. The plan for today is we first of all finish the practice question for chapter 5. Okay, we have about 4 questions remaining. After that, we'll start talking about chapter 6, which is the last major chapter for this class. Okay, so chapter 6 is hypothesis testing. Okay. All right. So last time we stopped at question number 5. Today, question number 6 on page 364, question number 10. Okay. So again, look at the last sentence of the question here. So find the 90% confidence interval for difference between percentage. Okay. So that is confidence interval for difference between two proportions, because percentage and proportion talk about the same thing. Okay, so let me write down the equation first. So that's CI for difference between two proportions. Okay. So Px minus Py, so that's the difference between two proportions. Okay. Modify Px and Py, so that's the sample proportion. Okay. Plus minus z half alpha. It's Px. Let's modify Px and modify Nx. Okay. Modify Py. And modify Ny. Okay. And also we have the equation for Nx and Ny. Px and Py. Okay. So the equation is from page, as equation number 518 on page 361. Okay. And also the range for the difference between two proportions should be between -1 and 1. Okay. So cannot be outside this range. All right. Then let's read the question together. We have article evaluation of criteria for setting speed limit on gravel roads. Okay. So this is about transportation engineering. So counted number of vehicles on various types on several roads in the state of Kansas. Okay. So in Ready County, 13 out of 67 vehicles on Wattsburg Road were heavy vehicles, while 32 out of 91 on another road were heavy vehicles. So asking for the 90% CI for difference between these two proportion, these two percentage. Okay, so again, based on the equation, we just need to figure out the numbers. Okay, so x 32, nx 91. Okay, so modified nx, so that is 91 plus 2. Okay, and modified px based on the equation 32 plus 1 over 91 plus 2. Okay. So same thing for y, 13, and y, 67. So modify y and y, 67 plus 2 is on the equation, and modify py, 13 plus 1 over 67 plus 2. Okay, and then z half alpha. Okay, because this is 90% confidence interval, half alpha will be 0.05. Okay, so 100 minus 90 is 10, divided by 2 is 5, so 0.05. Z 0.05 will be 1.645. So that is from
That's
here.
always.
No, I don't think anyone looked that up.
Okay. So then we plug the numbers into that equation here, into this equation. We can figure out the range. I will skip the details. This is the answer. So 90% CI for difference between these two proportions is between these two numbers. Okay. So that's question number 10. Next, page 375, question number 9. So that is from section 5.7, I think, pair data. Question number 9. Okay, so question number 9 is here. Look at last sentence, A, find 99% CI for the mean difference in fuel economy. Okay, we can see we have tables here. Okay, from table we have 9 cars and 18 cars. Okay, Chap A and Chap B. Okay, from there we know this is for pair data, which means for a single item we measure 2 different things. Okay, there's 1 pair, 2 pair, so different pair. Okay. So then let's read the question. Okay, so a tire manufacturer is interested in testing the fuel economy for 2 different tread patterns. Okay, so similar to one of the questions we discussed before, tire of each tread type are driven for 1,000 miles on each of 18 different cars. Okay, so 18 different cars. So we have 18 pairs. And here the table shows the mileage in MPG in this table. Okay, 2 types of Chap A and Chap B. So we have 18 pair data. Okay, so again, first of all, let me use the equation for that. So this is CI for pair data. And depending on the sample size, we either use t-value for small sample or z-value for large sample. Okay. So mu x minus mu y equal to, okay, so this is the average for difference between the pair data. Okay. So when the sample size is small, we use t-value. For t-value, we have 2 parameters. One is the degree of freedom. In this case, it is n-1, and the other one is half alpha. Okay, so that's t-value, and then sample standard deviation and sample size n here. So this is n less than 30. When n is larger than 30, we use the z-value. For z-value, we only have half alpha, 1 parameters. Remaining will be the same, sample standard deviation and the sample size and here. Okay. Right, so this is equation 524 and 525 on page 373 of the textbook. Okay, so in this we have 18 cars, so less than 30, less small sample. We should use t value, t table, t score. Sorry. So first, let's calculate all these parameters. This is the average of the difference. Okay, so what we do is for car number 1, okay, so thread A is 24.1 mpg, thread B is 20.3. So difference is 24.1 minus 20.3. This is 3.8. Okay, so then we take the average of this 18. Okay, and we calculate this. So average of the difference for these 18 cars. So it's 1.744. Okay, and similarly we can calculate the standard deviation for the difference. Okay, so it's 1.46. For t value, okay, so n minus 1 is 18 minus 1. Okay, for 99% CI, half alpha will be 0.005. Okay, and from table 8.3, that value, the t value will be 2.898. Okay, so make sure you can find that number yourself. Okay, so you can please double check. 2.898. So then we just plug in the number. Okay, in this first equation, we can get answer for 99% confidence interval is between 0.747, 2.742. Okay. Yeah. Okay, so part A, question number 9 for part A. Okay, so we don't need to do the part B. Let's do the next question, question number 10. Okay. Yeah. Question number 10. So refer to exercise 9. So refer to the previous question. In a separate experiment, okay, 18 cars were outfitted with tires with tread type A, and another 18 cars were outfitted with tire with tread type B. Okay, and then each car was driven 1,000 miles. Okay, so the car with tread A averaged 23.93 mpg, standard deviation of 1.79. The cars with tread type B averaged 22.19, standard deviation of 1.95 mpg. Okay. So question A. So which method should be used to find the confidence interval for the difference between the mean mileage of the two tread type? Okay. So should we use pair data? Okay. If not, what equation we should use? Okay. So for pair data, remember it should be two different type of item, two different type of measurements in one sample. For example, car number 1, we have two different measurements, tread A and tread B, two different mpg. Okay. For question number 10, we have 18 cars with tread type A and another 18 cars with tread type B. Okay. So that's two independent samples. This is not pair delta. Okay, so we cannot use the equation for pair delta to resolve this question number 10. Okay, so what equation we should use then? Okay, so this is not pair delta, but the question is asking for confidence interval for difference between two mean value. Okay, one is for trap A, the other one is for trap B. Okay, so that is confidence interval for difference between two means. And then we can look at the sample size, 18 cars. Okay, small sample. So that is small sample confidence interval for difference between two means. Okay, which we discussed before last time, okay, which is here. So small sample confidence interval for difference between two means. Okay, so do not use the wrong set of equation. Okay, so we use this equation. That equation, we need to calculate the mean value and then the t value. Okay, for t value, the degree of freedom is V. V has its own equation to calculate that. Okay, it's very complicated, but easy to follow, as you see. Then half alpha is the same sample standard deviation Sx and Sy, and sample size Nx and Ny. Okay. Okay, so let's use this equation, small sample confidence interval for difference between two means, to resolve question number 10. Okay. Mean value, standard deviation, all given by the question. Okay. Then the number of freedom, okay, is very complicated. I don't want to waste our time here, but use this equation, plug in the number for Sx, Sy, Nx, and Y, and we calculate the degree of freedom. Okay. It's around 33, okay, because we need to round it to the nearest integer. Okay, so the t value will be 33 degree of freedom, 99% confidence interval. So half alpha will be 0.005. Okay, from table 8.3, the number is this. Okay. This, and then we plug in the number into this equation. Okay. So answer will be this. Okay. So for chapter 5, it is easy to see. Okay, depending on the question it's asking. Confidence interval. Okay, we have about 7, 8 different set of equations. Choose the right one, and then remaining will be very straightforward. Okay, but sometimes it could be tricky, such as this question number 10. You should know this is not pair delta. This is for two independent set of delta. Okay, so difference between two mean. Right. So that's question number 10 here. Then the last question. So this is about a prediction interval and the tolerance interval. Okay. It's not confidence interval, but the equations are similar. Okay. Page 384. Question number 2. In section 5.9. So we have a sample of 20 volts. Question number 2. The average breaking torque 89.7 J, standard deviation 8.2. Assume that breaking torque are normally distributed. Okay, so that's the condition. To use prediction interval and tolerance interval, the distribution need to be normally distributed. Okay, so A is for 99% prediction interval, and the B is for tolerance interval for the breaking torque, including 95% of the bolts with 99% confidence. Okay. So again, the equation. So for prediction interval, so that is equation 5.26 on page 382. Okay. So prediction interval Pi is equal to the mean value for sample. Okay. T value, n minus 1 is degree of freedom, half alpha. Okay. S is the sample standard deviation. Okay. For tolerance interval, okay, so that is equation 529 okay, on page 384. Okay, so I tell you the details of this, so you can copy the equation and also its condition into a sheet of paper. Okay, so you can use them in hand during the exam. So TI, tolerance interval, sample mean. Okay. So T value has 3 parameters, N, alpha, and gamma. Okay, and then sample standard deviation. So that is table 8.4. 8.4. Okay. The first part for prediction interval. The sample mean 89.7, standard deviation on 2, sample size 20. Okay, so the T value n minus 1, n is 20, so that's 20 minus 1, half alpha based on 99% prediction interval, so half alpha is 0.005. Okay, so the T value is 2.861. Okay, so from table 8.3, make sure you can find the same number. Okay, so plug in this number to the equation for prediction interval. The answer will be For B, the tolerance interval, the mean value is still 89.7, S is still 8.2, doesn't change. Okay, N is still 20. Okay, so the key value is N, alpha, and gamma. Okay, so N is the sample size. So N is 20. Okay, alpha is based on 99% confidence. Okay, so alpha will be 0.01. Okay, and gamma is about how many percentage of the votes are included. So the question tells us 95% of the votes are included. So gamma will be 100 minus 95. Okay, so that's 5. So 0.05, 5%, 0.05. Okay, so from this, the table 8.4, the key value will be 3.1681. So that is table 8.4. Okay, so make sure you can find the same number yourself. Okay, so plug in the equation for tolerance interval here. So Ti will be this. Okay, so that's the last question for the practice session for chapter 5. Okay. Any questions before we start a new chapter, chapter 6? Okay, great. Chapter 6. Okay, so chapter 6 is hypothesis testing. Okay. You will see it is very similar to confidence interval. Okay. They have also 7-8 different situations depending on what kind of hypothesis testing we are trying to do. Okay. But first of all, what is hypothesis testing? Okay. What's the difference between hypothesis testing and confidence interval we learned from chapter 5? Right. So let's go back to one of the old problems in chapter 5. Okay. Remember we discussed one of the example in chapter 5 about microdrills and see how many holes the microdrill can drill before it fails. Okay. So in that example, we have a mean value of 12.68 holes the microdrill can drill before failure. Standard deviation is 6.83. Okay. So if we want to answer the question that whether or not the population mean life, mu, is greater than 11, which means if the new micro drill can drill on average more than 11 holes. Okay. So this is a very typical question we may ask. Okay. And then let's see what we can do. Okay. So we can address this by checking the value of the sample mean. Same thing I did as we did for confidence interval. Okay. So from the sample mean, we can see it is larger than 11. Okay. So 12.68 hole. So this is actually larger than 11. Okay. However, because we have uncertainty in the mean value, we have a difference between sample mean and the mean for the whole population. Okay. So that cannot guarantee that for the whole population, for all the new microdrill, the mean value is still larger than 11. Okay. So we would like to know how certain we can be that the population mean will be larger than 11. Okay. In this question, we are not interested in confidence interval. Okay. For confidence interval, we are interested in, for example, 95% confidence interval, the population mean will be between, for example, 11 to 14. Okay. We want to know here if the average is more than 11. So the statement, the population mean mu larger than 11 is hypothesis. Okay, and to determine just how certain we can be hypothesis is true, we need to perform a so-called hypothesis test. Okay, so in this chapter, we're gonna learn how we can set up a hypothesis test depending on the question. Okay. Section 6.1. Okay, so large sample test for population mean. Well, as you can remember, section 5.1 is large sample confidence interval for population mean. Okay, this is very similar to the first section in chapter 5. Okay, so for hypothesis test, we have a so-called null hypothesis. Okay, assumed to be true until we can prove otherwise. Okay, so let's read here. So see that the effect indicated by the sample is due only to random variation between the sample and the population. Okay, so what does this mean? So it basically tells us the sample does not reflect the population information. Okay, so and we call the null hypothesis H0. Okay. So let's keep reading. We have a so-called alternative hypothesis, okay, which will be accepted as true if we can reject or if we can disapprove H0. Okay. Says that the effect indicated by the sample is real in that it accurately represents the whole population. Okay. And we call alternative hypothesis H1. Okay. In other words, H1 says the sample does reflect the population information. Okay. So to perform a hypothesis test, so basically what we do is we put the null hypothesis, the H0, on the trial. Okay, and how to do that? Let's keep reading. To do the hypothesis test, we need to calculate a test statistics, such as a mean value, and also a so-called p-value. Okay. So the single statistics calculated from the sample, which will allow us to reject or not reject the null hypothesis H0. Okay. And we also calculate the p-value. What is p-value? The p-value is probability. So calculate based on the test statistics. Okay, and measure whether the test statistics is likely or unlikely, assuming H0 is true. Okay, and then we compare the p-value, the probability with a certain value. We call that alpha. Okay, if the p-value is less than alpha, then we reject H0. We say H1 is true. Okay. So that's basically the procedure we do a hypothesis test. Okay. Later on, we'll show you an example. So the conclusion for hypothesis test is either we reject H0 when the p-value is small enough, okay, or we fail to reject H0 if the p-value is high enough. And also we need to state about the reliability of our conclusion. Okay. So the question is, how can we reject H0 or not? Okay. So we calculate the p-value. And then we compare the p-value with the so-called significant level alpha. Okay, so alpha is the maximum tolerance risk we want to have to make a mistake. Okay, so if we decide to reject H0, so that's the level of mistake to reject H0. And typical value for alpha is 0.05. Sometimes the alpha is 0.01. Okay. All right. So we just discussed what is hypothesis test and what is the null hypothesis and what is the H0 and H1. Then let's look at the example. Okay. All right. So mayor of small city claimed that the average income in his city is 35,000. Standard deviation 5,000. Okay. And then we take a sample of 64 family. We found out the average income is only 30,000. Okay, much less than the mayor's claim of 35,000. Okay, so we want to check if the mayor's claim is correct. Okay, how we can do that? We need to perform a hypothesis test. We need to set up a null hypothesis, which is H0. Okay, so we assume the population mean is equal to 35,000, which is the claim of the mayor. So mu population mean, which is the mean income of the city. So let's just assume that's 35,000, which means in that case, the mayor's claim will be correct. And then H1 will be the opposite of H0. So which means the population mean will not equal to 35,000. Okay, which means the mayor will be wrong. Okay, so we start the hypothesis test by assuming the mayor's claim is true and H0 is correct. Okay, so if we assume the population mean is 35,000, and then let's see what will happen. Okay, from a sample of 65 home, right, 64 families. Okay, the sample mean is only 30,000. Okay, and based on the central limit theorem, which is section 4.11. Okay, this is large sample. Okay, the mean will follow a normal distribution. Okay, with the mean value of 35,000. Okay, and the standard deviation of so which is the function of sample standard deviation and sample size. So 5,000 over sample size is 64. So that is 625. Okay. So the variance will be 625 squared. So this is the null distribution. All right. So if we assume the mayor's claim is correct, and then the population will follow a normal distribution of this. Okay, and then we can calculate the z-score for 30,000. Okay, so the z-score for 30,000, okay, based on the z-value. Okay, so x minus mean divided by sigma, or sample standard deviation. Okay, so mean value is 35, as we assume, and the sigma is 625. Okay, so calculated z-score is -8. Okay, and we know for normal distribution, okay, mu 2 mu minus 2 mu. Okay, so we have a so-called 68%, 95%, and 99.7% rule. Okay, so which basically means for mu plus minus, sorry, not mu, sigma, sorry, sigma. Okay. So we have 63% fall within mu plus minus 1 sigma. Okay, and for mu plus minus 2 sigma, so that is 95%. And for mu plus minus 3 sigma, okay, so that will be 99.7 or 7%. Okay, so the z-value we calculate is minus 8, which means this is less than 8 standard deviation below the mean. All right. Okay, so that tells us the probability of observing a sample mean of $30,000 if the mayor's claim is true is very, very small, nearly 0. Okay, minus 8 sigma. Okay. And then we can claim mayor's claim is false. Okay, and each one will be true. So based on empirical rules for values more than 3 standard deviation, okay, so that is 99.7% away from the mean will be considered extremely unlikely. Okay, in our case, we have 8 standard deviation away from the mean, okay, which is extremely, extremely unlikely. Okay, so such a value will be extremely unlikely to occur if indeed A0 is true. Okay, and so we have very good reason to reject H0. Okay, and because the observed sample mean of $30,000 is so unlikely if we assume the mayor's claim is true, so we choose to reject the mayor's claim, which is H0. Okay, so we reject H0 when the population mean is 35,000. So we can conclude that the mayor's claim is incorrect. All right. So we just discussed a sample of hypothesis test. Okay. All right. So for large sample hypothesis test for population mean, okay, of course, the requirement is the sample size is larger than 30. Okay, mean value, mu, and standard deviation of sigma. Okay, sometimes the sigma is known, which is the population standard deviation. If it's not known, then we can use sample standard deviation S to guess the sigma, okay, because the sample size is large. Okay. So the hypothesis test to be tested is we need to define H0, okay, which is the population mean equal to a certain value. Okay. In the previous case, that value is $35,000. Okay, all the value we want to check. Okay, so versus H1, which is alternative hypothesis. Okay, so the alternative hypothesis will be the opposite of H0. Okay, so mu not equal to mu0, the certain value we want to check. the test statics in this case will be the z-value. Okay. So assume if 0 is true, we need to check the z-value. Okay, so the equation not show very incorrect form. So let me rewrite this. The z-value will be the sample mean minus mu 0. Okay, so mu 0 is the value we want to check, such as $35,000 in the previous case. Sigma, okay, square root of n. Okay. If we do not know the sigma, we can use sample standard deviation, S. Okay, so the test statics in this case will be the z-score. This is because x follow a normal distribution with a mean value of mu 0 and standard deviation of sigma over square root of n. Okay, so this is based on central limit theorem. And we call that no distribution. So we need to calculate the z-score. Okay. So if x0 is true, then the value of x should be close to the mean value, mu 0. Okay, and the z-score should be pretty small, or close to 0. Okay, so if x0 is not true, then the x will be either much larger or much smaller than the mean value mu 0. Okay, so the z-score will be either very large or very small compared to 0. Okay, so if the z-score fall within a so-called rejection region, because it's either too large or too small, then we should reject H0. Okay, so again, first of all, we calculate the z-score based on the equation here. Okay, and then we calculate the p-value. Okay. So if the p-value is small enough, smaller than a preset number, which is alpha, normally 5%, sometimes 1%. So if the p-value is small enough, then we should reject H0 and we conclude H1 is true. So after we calculate the test statics, in this case the z-score, then we calculate the p-value. Okay, so the p-value is the probability. Okay, the full definition of p-value is here. So p-value is probability of observing just by chance a test statics as extreme or even more extreme than what we have actually observed. Okay, so if H0 is rejected, this is actual probability that we have made an incorrect decision. Okay, so the p-value is the probability we make a wrong decision. Okay, so the probability should be small enough. Okay. A typical value for a cutoff value will be 5%. So if this probability is very small, okay, smaller than a pre-assigned significance level alpha. Okay, again, alpha will be 1% or 5%. Okay, so if the question tells us an alpha, then we need to compare the p-value with that alpha. if the question doesn't tell us alpha, normally we assume the alpha to be 5%. Okay, so if the p-value less than that alpha, then H0 can be rejected, and we say H1 is true. H1 is true. So the procedure is pretty complicated. So let's reiterate the procedure again. Okay. So we began by assuming that H0 is true, such as in the previous example, we assume the mean income for the city is 35,000. Okay. This is similar to began a trial by assuming that a defendant is innocent. Okay. And then we get a random sample, such as the average income of 64 family. So the sample gave us the average income of $30,000. Okay. And a hypothesis test involved measuring the strength of the disagreement between the sample, for example, the 64 average of 64 family income, $30,000, and H0, okay, which is the population mean is 35,000. Okay. So we measure the strength of disagreement between the sample and H0 to produce a number between 0 and 1. Okay. So in the previous case, we calculated the z-score. The z-score is around -8. So the probability is very, very small. Okay. And that number, we call that p-value. Okay. And definition of p-value is here. Okay. So the p-value measure the plausibility of H0. Okay. So the smaller the p-value, the less plausible H0 is true. So we have a stronger case to reject H0, and we conclude H1 is true. Okay. So smaller the p-value, the stronger the evidence is against H0. And if the p-value is sufficiently small, again, how small it is, we compare to alpha. Okay, alpha, for example, 5%. Okay. So if p is sufficiently small, we may be willing to abandon our assumption that H0 is true, so we believe H1 is true instead. Okay, and we call this rejecting the null hypothesis. So the null hypothesis is H0. So rejecting H0. Okay, so steps. The first step, we define the null hypothesis H0, and then the alternative hypothesis H1. Okay, so I can tell you a trick how to do the definition depending on how the question is asking. Okay, later, next time. So the first step is define H0 and H1. And then let's assume H0 is true. Okay. And then the third step is we calculate a test statistics, okay, such as z value. Okay. So the test statistics is the statistics that is used to assess the strength of evidence against H0. Okay. And then based on the test statistics, we calculate the p-value, which is the step number 4. Okay. All right. Again, the p-value is the probability assuming H0 is true. Okay. And the p-value is also called observed significance level. Okay, and then we compare the p-value with significant level alpha. Okay, if it is less than alpha, then we can draw a conclusion. We either reject E0 or we do not reject E0. Okay, so let's look at another example before we dismiss today. So daily yield for a chemical plant has average of 180 tons for several years already. Okay. So the quality control engineers manager want to know if this average has changed. Okay. So she take an example. Okay. She select 50 days and records average of 871 tons years. Standard deviation is 21 tons. Okay, so the average is smaller to the old average, 880, but close enough. Right. So first of all, we need to set up the null hypothesis H0 and the H1. Okay, so basically we should first set up H1 as whatever the question is asking. Okay, so the question want to know this, if the average has changed. Okay, so if the average changed, it means the population mean will not equal to the old average, which is 880. Okay, so the first trick is set up H1 as whatever the question is asked. So what the question is asking. Okay, so that is H1. In this example, the population mean not equal to 880. And then the null hypothesis will be the opposite of H1, which means the population mean will equal to 880. Okay, so that's first step. And then we check the Z score. The Z score is okay. So the sample mean is 871. Mu zero is 880. 880. Sample standard deviation is 21 times. The sample size is 50 days, 50. Okay. So the Z-score is minus 3.03. Okay. So it is very small Z-score. So what is the probability that this test statistics, which is Z-value, okay, or something even more extreme, okay, even far from what is expected if H0 is true, could have happened just by chance. Okay, so the p-value is probability H0 is true. Okay, and we calculate that, okay, because the Z-score is minus 3.03. Okay, so the p-value will be extreme or even more extreme than minus 3.03. Okay, so that including the left-hand tail and right-hand tail. Okay, so the p-value is equal to the probability for Z larger than 3.03 plus the probability for Z score less than minus 3.03. Okay, and based on table 8.3, the Z table, so the p-value is very small. Okay, 0.0024, so 0.24%. So that means this is an unlikely occurrence. Okay, so only happens 2 times for every 1,000 times. if you assume the mean value is actually 880. Okay. All right, so let's stop here. Today we finish the chapter 5 practice questions. We start to introduce hypothesis test. The next 2 or 3 class we'll finish chapter 6, and then we do some practice session for chapter 6, and that's toward the end of this semester. Okay, so let's stop here today. I will see you next time.